Okay, welcome to my class, the Advanced Analysis of Solid and Structure. We have only 6 or 7 students here. So, do you have a syllabus? Okay. So, the name of this class is Advanced Analysis of Solid and Structure. Until last year, the name of this class was Nonlinear Analysis of Solid and Structure. So, but contents are all the same. So I changed the title because many students don't like the word nonlinear. So advanced is much better. So I am Pilsung Lee, instructor of this class. Also, I am a professor in Ocean System Engineering Department. Introduction. So, objective of this class is to provide the unified understanding of solid and structural mechanics. So, in other department of KAIST, the structural mechanics class and solid mechanics class are different. So, they are separately teach both class, but in our department, I'm only an instructor to teach both area. So I like to give you both. So I like to provide unified understanding and teaching. And first, this course will teach the fundamental concept of solid mechanics. So on deformation, strain, stress, strength, and elasticity, and plasticity. This is all about solid mechanics. So for the half of this class, first half, I'm going to teach this thing, and then the governing equation. And after introducing the reduction procedure, I'm going to read the concept of structural mechanics, tensioning, bending, shearing, and twisting. And I like to introduce the simplified governing equation for structural mechanics. And through the lectures, various solution procedure, displacement and stress method, and principle of virtual work, energy method, and direct stiffness method. Also, in the last part of this class, I will deal with some nonlinear topic and collapse analysis and structural stability about buckling. So you can see the class schedule. We have 16 weeks. We have 1 week for midterm exam and 1 week for final exam. So actually, for lecture we have 14 weeks. References. So we have 4 textbook, mechanics and durability of solid, and finite element procedure, in elastic analysis of structure, in elastic analysis of solid and structure. You don't need to buy all of these books. So I think the class will be enough. But if you want, you can buy and then read these books. So grade policy, homework 20%. So about 10 homework we will have. There are going to be a midterm exam 30%, final exam 50%. So homework, midterm exam, final exam, all the important. Especially final exam is the most important. Okay, so okay, let me introduce the class, the subject I'm going to teach. Advanced analysis of solid and structure. Okay, advanced analysis of solid and structure. Let me define the structure. So, what's the structure? Actually, I studied and doing research on the structure for a long time, about 15 years, but I never thought about what's the structure. I never defined the structure by myself before. So 3 years ago, when I started this lecture, I tried to understand and try to define what's the structure. Okay, this is a very quite difficult question. So there are going to be many definitions about the structure, but I define like this. This is a system to keep a shape. Under interaction with its surroundings. So this means that everything you can see are structured. So your body, your hair, this building, okay, cell, from the very tiny thing to the very big thing, universe, all the structure, okay, they have a shape. And it is interact with its surroundings. So, for example, so wind, wave, and other kind of external force, right? Okay. So in nature, we have a structure, three cell structure, right? And body and earth. A lot of structures exist in nature, and we are engineers, so let me talk about engineering structure. Mechanical, so structure in mechanical engineering, so automobile, airplane, and the part of automobile engine. These are the old structure, and civil engineering structure, the little bit big, bridge, building, and plant, some tower. So, in our department, ocean engineering structure, ship, and submarine, and jacket, breakwater, and so on. So, in engineering, we have a lot of different structure. Especially the mechanical engineering structure is a size is less than 10 meter. And civil engineering structure is very huge. So it has a order of 100 meter to kilometer, right? 1 or few kilometers. So and kilometers, and ocean engineering structure have also order of 100 meters. So 100 meters, 200 meters, and 300 meters, something like that. So order of size are different. Okay. So now we define the structure, and I gave you an example of structure. Now let me define the structural engineering. Structural engineering. So I'm structural engineer. So here in this class, some of you are structural engineering, or some of you wanted to be a structural engineer, right? So this is a series of work to find safer and more cost-effective structure. So in structural engineering, there are very important keywords. First keyword is safety. Okay? Safety is the most important keyword in structural engineering, because we are living in, on, or around the structure. If the structure fails, some people can die, right? So safety is most important. And then cost effectiveness is important, because this is engineering, right? We need to produce the cheap structure, right? Cheaper structure, and structure mechanics. Mechanics deals with the fundamental. So structural mechanics deals with the fundamentals of structural engineering. So fundamental means some mathematics and theory and physics. So, engineering graduate school, you are student in engineering school, right? KAIST is engineering school. So let me introduce what we need to do in this engineering school. Okay? First, we have some real problem. This is a problem we need to solve. For example, you wanted to know the temperature variation of this room. Okay? That's the real problem. Maybe your advisor wanted to know. Okay? And then, second, assumption. Real problem is very complicated, right? The temperature variation of this room depends on a lot of different factors, right? Outside temperature and number of people here, shape of this room, right? And the capacity of a heater. So a lot of factors are related with the real problem. So first of all, we need to make some assumption. Okay, we need to pick up some parameter which govern the real physics or problem we have. Okay, so this assumption process to make an assumption is very important. And third, with that assumption, we make a mathematical model. So we can express the real problem with some equation, right? That equation is a mathematical model. So usually that equation have a forms of a differential equation. Especially partial differential equation. We are saying this is a governing equation. And fourth, so once we have a proper mathematical model, then we need to find the way to solve this mathematical model. So there are two procedures, analytical or numerical. Numerical procedure to solve PDE. So if the mathematical model is simple, the problem you want to solve is simple, we can use a analytical procedure. So I mean that you can solve that problem very simply by your hand, right? Pencil and paper. So you can simply solve. But in real world, the most problem is very complicated. So we need to use a numerical procedure. For example, FDM, finite difference method, or FEM, finite element method. Both are the very nice example we can use to solve this kind of problem. and 5. Then we can solve. So let's solve. Solve the problem. Okay. So now we solve the problem. Is that all? No. Last procedure is you need to understand. Understand the solution. Okay. We need to check whether the problem is properly solved or not. This is a very important procedure. Okay? So, okay, so I like to give you a note. It is very important to understand the assumption and mathematical model. So, used. Otherwise, we are not able to so it's very important to understand the assumption and mathematical model we choose or we use. Otherwise, we are not able to validate the solution. Okay. So when we try to understand the solution, we always keep in mind what kind of assumption and what kind of mathematical model we use. Because the solution, okay, we calculated is a solution of the mathematical model under some assumption. It's not a solution of real problem, okay? It's not a solution of a real problem. It's just a solution of the mathematical model. So if the mathematical model and assumption is limited or it's not proper, so solution is also not proper. So I mean the solution cannot show the real phenomena. So let me give you example. So cantilever beam problem. This is one of the easiest example in structural mechanics. Here we have a fixed end and straight and prismatic cantilever beam we have here. Let's say length of this beam equal 5 meters, and we apply some force P equal 1 ton. So in undergraduate school, we use some assumption to solve this problem. What kind of assumption did you use? You remember? Assumption. We used a lot of assumption. For example, for material. Regarding material. TA. What? Huh? Isotropic. Okay, so we use the assumption isotropic and homogeneous and linear elastic. And so on. In undergrad school, we use the assumption isotropic, homogeneous, linear elastic for the material. You know the meaning? Homogeneous means the material, property of a material is uniformly distributed. Okay? So property of material does not depend on the position in the space. Okay? And isotropic means the property of material does not depend on the angle, direction. And I think that most of you know about linear elastic, right? So I will give you a first homework about the definition of this word. Okay? So I hope you know the exact meaning of this important word. In structural and solid mechanics, there are a lot of important concepts. Like I said here, okay, isotropic, homogeneous, and linear elastic. Okay, you need to understand the exact meaning. Okay, and for kinematics, we use the assumption small displacement and small strain. Okay, and especially in undergrad school, we use the no transverse shear deformation. This is a part of the assumption of Euler and Bernoulli beam theory. So, for that simple cantilever beam problem, we use the assumption about material kinematics quite a lot, right? Based on this assumption, we can make a mathematical model. This is mathematical model for that beam problem. Here the W is a transport force, okay, W, and delta is a deflection. Delta is a deflection. This is a function of x also. And also boundary condition. And boundary condition. Boundary condition is also part of the governing equation and mathematical model. What kind of boundary condition? W, x equals 0 with 0, right? And rotation. X equals 0 equals 0. So also we need to have a boundary condition about the force. So in this problem, displacement boundary condition and force boundary condition. Okay, and we need to, how to solve this equation? So mainly we need to solve this partial differential equation, okay, with that boundary condition, right? So this example is very simple. So we can solve this problem analytically, very simply. So how to solve? So we can solve analytical way. Because this problem is very simple, analytical method. So then we need to check the solution. So we need to check whether we have a meaningful solution or not. For example, we have a displacement at the tip is 100 meters. Okay? Is this a proper solution or not? We can check it. So length of beam is just 5 meters, but tip displacement is 100 meters. This is a clearly very, very large displacement, right? So, but we use the assumption, small displacement. So if we get the large displacement, okay, we can say that solution is totally wrong. We cannot use, right? For example, tip displacement is 0.1 meter. Then we can think it cannot make sense. It can make sense, right? Okay, so this is just an example. In structural mechanics and solid mechanics, there are a lot of basic concepts. So we need to know a lot of stiffness and strength and flexibility. You need to understand what's the stiffness, what's the strength, what's the flexibility, and stress and strain. Strain, and also regarding material, homogeneous, non-homogeneous, isotropic, non-isotropic, elastic, inelastic, and plastic, elastoplastic, static, dynamic. And least you need to understand. You need to know the exact definition and meaning of all of this word. Okay? Stiffness. Yeah, everybody knows stiffness, but if I ask what's the definition or exact meaning of stiffness, then nobody answers. You know, stress. Everybody knows the stress, but nobody can answer what's the stiffness, right? What's the difference between static and dynamic, right? But at least all of you here in this class, okay, should understand the meaning of this word. Okay, that's your work. And through this class, your understanding become better and better, and you will understand. But before I'm gonna give you a first homework about definition of this word, and you can try to understand all of this word, okay? And okay, let me start the main lecture. This is all about introduction. In mechanics, we always should describe some quantity, right? What kind of quantity we are dealing with? Okay, here the stress strain, these are also quantity. Pulse, displacement, okay? Temperature, these are all the quantity we need to use, we should use in mechanics to represent that quantity, we are using the vector matrix and tensor. So you are very, very familiar with vector and matrix, but not familiar with tensor. Is that right? Scalar. Scalar is what's most basic thing. Let's say there is a scalar alpha. Scalar. What's the scalar? Scalar is a physical quantity. That can be completely described by a real number. Okay? So it's a physical quantity. Can be described by one number, one real number. Example, TA. Can you give an example of scalar? Length. Okay. And number of girlfriend. That's also scalar. Okay. And temperature. And number of something, right? Is a scalar. So everybody already well know about scalar and vector. Vector is a little bit difficult thing. So this is a array of n number. Ordered number. So vector is an array of n number. So array of scalar. Okay, so expression so usually I like the first one. We can write some arrow under the character, and we can use some bold character, and we can put on the bar, and we can use a component form, something like that, A1, A2. AN. So here A1, A2 are number, right? Scalar. So I put the n number with the array. So vector is a set of scalar. Okay? Ordered number, an array of number. So we are using the vector when we describe the velocity force moment displacement something like that. And matrix let's say we have a matrix A. It's an array of ordered number. So ordered number is a vector, right? So matrix is an array of vector, right? Vector is an array of scalar. Matrix is an array of vector. So we can put the two arrow and bold 2 on the bar. In component form, we can use table A, N, and something like that. This is a matrix. So let's see here. This is a vector, right? Column vector. Second column vector. So if we use many column vector, if we assemble the many column vector, we can make a matrix. Example, stress and strain. Stress and strain is a physical quantity which can be described by matrix. Actually 3 by 3 matrix. Okay. So here, so vector, scalar, vector, matrix are the physical, some way, method to represent a physical quantity. And we know the some simple rule, okay? Scalar is all real number, single real number. Vector is an array of scalar. Matrix is an array of vector. There are going to be an array of matrix, right? And array of matrix, right? So I'm going to talk about that much more generalized physical quantity in the next lecture. Okay? Thanks.